Welcome back to the deep dive. Today we're cracking open a problem that honestly feels a bit like a party game at first,
Yeah, it really does.
but it ends up being this incredible masterclass in resource allocation. We're looking at reorganized string.
That's Leak Code Problem 767 for anyone following along at home.
Right. And for a medium difficulty problem, this one punches well above its weight class in terms of the concepts you have to juggle.
It absolutely does. It's one of those problems where the brute force solution is an absolute nightmare, but the optimal solution makes you feel like an absolute genius.
Oh, for sure. So our mission today is to figure out if a valid arrangement of a string even exists, and if so, exactly how to build it.
Because we're essentially dealing with a constraint satisfaction problem,
Yeah.
but it's disguised as basic string manipulation.
Exactly. And just to give a quick overview of our sources today, we are pulling from algorithmic breakdowns on AlgoMonster, some data structure guides from Codecademy, and of course the core problem definitions from LeetCode.
It's a great mix of theory and practical implementation.
So to set the stage for you listening, we are not just randomly shuffling letters here. Think of it like a dinner party seating chart.
Oh, I like that analogy.
Right? So you have a list of guests, which are the characters in your string, but some of your guests are identical clones. They're the exact same letter.
And the one golden rule of this dinner party is that no two identical clones can sit next to each other.
Right, they need a buffer. So if you have the string AAB, you can successfully rearrange that to ABA. The neighbors are different.
But if you get a string like a B,
Then you are in trouble.
you are. It doesn't matter how many times you shuffle those seats, two A's are always going to end up touching. So in that case, the algorithm just has to return an empty string.
Failure case. So before we even attempt to move characters around, and I see developers trip up on this all the time, there's a math check.
The sanity check.
Yes, you have to ask, is this even mathematically possible before you burn a single CPU cycle trying to build an output?
This is such a crucial first insight from the AlgoMonster source. There is a hard threshold. If the frequency of your most common character is too high, the task is just impossible.
And the formula they highlight for this threshold is the string length n+1 and then integer divided by 2.
Right, so n+1 floor divided by 2, that gives you the ceiling. If your maximum character count is greater than that number, you instantly fail.
I want to pause on that formula for a second because I feel like a lot of people see that and try to use regular division, or they try to import a math library to do a ceiling function. But the integer division is so much cleaner.
It really is. It completely avoids any weird floating point issues.
Well, why the +1? Why not just n divided by 2?
Okay, so think about a string of length 5. You have 5 seats at the table.
Okay.
Those seats are at indices 0, 1, 2, 3, and 4. If you want to place identical characters as far apart as possible, you put them in the even-numbered seats.
So 0, 2, and 4, that's 3 seats.
Exactly. Now, if you just did 5 integer divided by 2, you would get 2. That would falsely tell you that placing 3 characters is impossible.
Which is the classic, off by 1 error, just waiting to ruin your day.
Right. So by doing 5 plus 1, which is 6, and then dividing by 2, you get 3, it perfectly calculates the capacity of those even indices for odd-numbered lengths.
That makes perfect sense. It's essentially checking if the majority element can fit into the majority slots. If you have 4 A's and only 5 seats, they will overlap.
Period. No matter how clever your algorithm is.
So assuming we pass this validity check, we count our characters, we find the maximum frequency, and we confirm it doesn't broke that threshold,
Right.
we now have permission to actually try and solve the puzzle.
We need a strategy.
And the sources all point toward greedy algorithms. Now, I feel like greedy is a bit of a loaded term in computer science.
It usually implies a sort of short-sightedness, like you're grabbing the biggest piece of cake right now without realizing you might starve later.
Right. But in this specific context, being greedy is actually the safe play.
It is. A greedy approach just means making the locally optimal choice at every single step. And here, the optimal choice is to deal with the character that is causing the most pressure.
The loudest guest at the dinner party.
Exactly. The one with the highest frequency. If you have 1,000 A's and 10 B's, and you decide to place a B first because you want to save the A's for later,
You are digging your own grave.
you really are. You have to burn down that highest frequency count as quickly as possible to keep the remaining puzzle valid.
So step 1 of our actual process is sorting our characters by their frequency. We don't care about alphabetical order at all here. Z does not matter more than A unless Z appears more often.
We are entirely reliant on a frequency map. You map the counts, and then you process the string based on those counts.
Which brings us to the first of the two main implementation paths. The spatial approach, or what the outline calls the alternating index strategy.
I love this approach. It feels very close to the metal. You're almost manually managing memory layout.
It's very tactile. You create an empty array for your result, and you just start filling the even buckets first, 0, 2, 4, 6.
Because that guarantees maximum separation. If you take your most frequent character, let's say it's A, and you put it in every other slot starting from 0.
You inherently place a buffer between them.
Exactly.
So let's walk through an example to visualize this. Let's take the string ABBC, so length is 6.
Okay, so our most frequent character is A with a count of 3.
We place those at indices 0, 2, and 4, so our array looks like A blank A blank A blank.
Then we grab the next most frequent, which is B. It has a count of 2.
Now we are out of even slots, right? Because index 6 is out of bounds.
Right, so the algorithm just switches to the odd indices, 1, 3, 5.
So we place the B at index 1 and index 3. Now the array is A, B, A, B, A blank.
And finally, we have 1C left. We put it in the last remaining odd slot, which is index 5.
Resulting in ABA, BAC, which is perfectly valid. No neighbors match.
It's extremely efficient. But there is a massive trap here that AlgoMonster explicitly warns about, and it's worth highlighting for anyone prepping for an interview.
Oh, the string concatenation issue.
Yes. In languages like Python or Java, strings are immutable. You cannot change them once they are created.
So if you sit there in a loop doing result string plus equals character, you are copying the entire block of memory every single time you add a letter.
It turns what should be a fast linear time operation into a quadratic disaster.
Big O of n squared.
Right. If your string is 10 characters long, you won't notice. If it's 100,000 characters long, your program's going to time out and crash.
So the fix is to use a list in Python or an array in Java or C++. You treat it as a mutable buffer, fill the slots by index, and then just do one single join operation at the very end.
That is critical here because the alternating index strategy is jumping around. You aren't just tacking letters onto the end. You're placing them at 0, then 2, then 4. You have to have a random access data structure.
Okay, so that's the spatial approach. It's direct, it's fast, it runs in O of n time, but it's not the only way to solve this.
No, and for a lot of people, it's actually not the most intuitive way either. The second approach uses a specific data structure, the max heap.
This is the one that Codecademy really dives into. And it's the pattern that shows up in a ton of similar, more difficult problems.
It's a much more dynamic way to manage the queue.
So for anyone who needs a quick refresher, a heap is essentially a binary tree where the parent node is always greater than or equal to its children.
Think of it like a strict corporate hierarchy. The CEO, the highest value, is always sitting right there at the top desk.
So you have constant time access to the maximum element. You can just peek at the root.
And even though we draw it as a tree, it's usually stored under the hood as a simple flat array where the parent-child relationships are just calculated using index math. So it's very memory efficient.
So how do we apply this hierarchy to our dinner guests?
We put all our character counts into this max heap, often called a priority queue.
So the character with the highest frequency is always sitting at the top, ready to be popped off.
Right. So we enter our main loop. Step 1, we pop that most frequent character. Let's say it's A. Step 2, we add A to our result string.
Makes sense. But here's the catch. We used an A, but we might still have 5 A's left. We can't just put the A back into the heap right now, can we?
No, because the heap will do exactly what it's designed to do. It will sort it right back to the top.
Because 5 A's is still probably more than the 3 B's waiting in the wings.
And if it goes back to the top, your next loop will just pop another A. Now you have A in your string, and your algorithm has failed.
So we have to artificially circumvent the heap's natural behavior. We need a cooldown period.
The waitlist. Once you pop a character and use it, you hold on to it, you put it in a temporary variable outside of the heap, you are effectively banning it from re-entering the queue for exactly 1 turn.
I love the dynamic here. You lock the VIP in a side room, then you go back to the heap and say, okay, who is the next highest?
And the heap gives you B.
So you pop B, you append it, now your string is AB. The neighbors are different.
Mission accomplished for that step, but now you have to manage the waitlist.
Right, because A has served its penalty.
Exactly. Since we just successfully placed a different character, A is now allowed add back in, so we push A back into the heap with its count decreased by 1.
And simultaneously, the B we just used goes into the waitlist.
It is a continuous juggling act. Pop A, hold A. Pop B, push A back in, hold B. Pop C, push B back in.
It's brilliant because it guarantees you will never place the same character twice in a row.
Mm,
Now let's talk trade-offs because these two approaches have different performance profiles.
they do. The alternating index method is strictly linear, big O of n. You iterate through the counts, you place the characters you've done.
But the heap method involves constantly inserting and deleting from a tree structure. That usually introduces a logarithmic factor, right? Log k.
Yes, theoretically, the heap operations take big O of n log k time, where k is the number of unique characters.
But practically speaking, what is k in this scenario?
If we are dealing with standard lowercase English letters, k is at most 26.
And the log of 26 is a tiny number. It's essentially a constant.
Right, so the asymptotic time complexity basically simplifies down to big O of n anyway. It's incredibly fast.
So if you were doing this with the entire Unicode library,
Thousands of emojis and obscure symbols.
then k becomes significant, and the overhead of the heap might start to drag your performance down compared to the spatial method.
That's a great edge case to keep in mind.
Space complexity is roughly the same for both, though, right? Big O of n to store the result string, plus big O of k for the frequency map or the heap itself.
Correct. They are very comparable in terms of memory footprint.
So why choose the heap method if the alternating index is slightly faster and maybe less code? And this brings me to the broader application. Why do we care about this beyond just passing a coding interview?
Because the max heap with a cooldown is a fundamental system design pattern. It goes way beyond string manipulation.
Codecademy points out task scheduling, and I find this fascinating. When I look at the activity monitor on my computer, there are hundreds of threads, but my CPU only has so many cores.
Right. So the operating system has a scheduler that has to decide who gets to run next. And it can't just run the most demanding task continuously.
Even if I'm rendering a massive video file, which is our highest frequency, a character, the CPU can't just give it 100% of the time.
Because if it does, everything else starves. Your mouse stops moving, your background email sync fails, the system becomes completely unresponsive.
And there's also the hardware level, right? If you just hammer the exact same memory registers or the same cache lines over and over.
You run into process affinity issues or resource locking. The scheduler is essentially playing reorganized string. It says, okay, video renderer, you are the most urgent. I will run you for one time slice.
And then into the waitlist you go.
Exactly. Even though the video renderer still has the most work left to do, the scheduler forces a context switch. It pulls a lower priority task, maybe a background download, lets it run for a microsecond, and then lets the video renderer back into the queue.
That is literally the pop-hold push cycle we just built.
It's the exact same logic.
And we see this in network routing too, right? Quality of service or QoS.
Absolutely. In a network router, you have packets waiting to be sent. Voice over IP packets are highly sensitive to delay. Those are your urgent A characters. File download packets are your B characters. They don't care if they arrive a few milliseconds late.
But if the router just dumped all the voice packets and ignored the file and download, the connection would time out.
So routers use algorithms like weighted fair queuing, which is basically a sophisticated max heap. It prioritizes the heavy urgent traffic, but constantly forces tiny gaps to let the smaller, less urgent packets through.
It's incredible to think that the logic keeping a video call from lagging is the exact same logic we use to keep the letter A away from another letter A in a string.
It really highlights how these foundational data structures scale up to solve massive real-world engineering problems.
Before we wrap this deep dive up, I want to throw one final thought out there for you listening. A sort of what-if scenario.
I love a good what if.
So we solve this for a distance of 1. A simply cannot touch A. But what if the rules get stricter? What if identical characters have to be at least k spots apart?
Ah, the rearranged string k distance apart problem. That's actually a known hard-level problem on LeetCode.
So does our spatial strategy, the filling the even indices and the odd indices, does that still work if k is 3?
No, it completely shatters. The entire math of the even-odd jump relies specifically on a distance of 1. If you need a distance of 3, you can't just skip one slot, you have to skip 2. And managing the wraparounds when you hit the end of the array becomes a nightmare.
What about the heap strategy?
The heap strategy handles it beautifully.
Really? How?
Think about our waitlist. For a distance of 1, our waitlist only needed to hold one character for one turn.
Right. We held it in a single variable.
If your distance rule changes to k, you simply upgrade that single variable into a queue data structure of size k.
Oh, wow. So you pop A, you put it in the queue. You pop B, put it in the queue. Pop C, put it in the queue.
And once that queue reaches its capacity of K, the oldest character at the front of the line finally falls out and gets pushed back into the heap.
You essentially just created a sliding window of ineligibility. The core logic, the greedy choice popping from a max heap, it remains completely identical. You just expanded the penalty box.
Exactly. And that right there is why I strongly recommend learning the heap approach, even if the index math is faster for this specific problem.
The heap generalizes to harder constraints.
It's a robust architectural pattern, whereas the index approach is kind of a clever one-off trick.
That is a phenomenal takeaway. If you're writing a quick script, use the math.
Mm.
If you're designing a system, understand the heap.
Well said.
But we have gone from seeding clones at a dinner party to balancing network bandwidth and CPU cores. I think we have thoroughly deconstructed problem 767.
It's always fun to see how deep the rabbit hole goes on these medium difficulty algorithms.
Absolutely. Thanks for joining us on this deep dive. Go optimize your queues, build some heaps, and we will catch you in the next one.